Okay, I think we're all here. So, it's a pleasure to get a chance to speak with you again. Last time I spoke, we were solving linear systems AX equal B with classical algorithms. Now that Nikhil has solved the small to moderate scale diagonalization problem for us, and Peter as well, maybe now we can think about large scale problems. So I'm shifting, and I'm imagining that we're going to now seek some subset of the spectrum of a large scale problem. So of course we're solving, and I'll just really address the standard eigenvalue problem, AV equals lambda V. And for A being very large, and in applications N may be in the tens to hundreds of millions or billions. It's impractical to diagonalize. Of course, we couldn't store a matrix V of eigenvectors. And so, nor would we want to. If you talk to Matt Colebrook, he'll talk about pseudospectral, about spectral pollution, and about the idea that when we have discretizations that give us such large-scale problems, oftentimes many of the eigenvalues are discretization trash, if you will, or artifacts of that discretization that are misleading, and we don't want to waste time computing those. And so we're looking for a class of algorithm that's going to zero in on some subset of the spectrum, and that's not just motivated by discretizations, but also by the kinds of problems that that motivate us to find eigenvalues in the first place. And so I'd like to begin by just speaking about three different problems that motivate our interest in eigenvalues. And so some that may be of a more, come from a different world may wonder, why do we even care about these things called eigenvalues in the first place? And so I'm beginning here, and A will always be, generally speaking, a real matrix, though not necessarily symmetric, and therefore potentially with complex eigenvalues and eigenvectors. And so at some points, I will need to use the star for conjugate transpose. And sometimes I'll just use the T for regular transpose, and correct me if I misstep. Okay, so problem one. X prime of t equals a x of t, and we are given some initial condition, the state of our dynamical system at time 0, and we would like to solve this evolution problem. And we'll assume throughout everything that I do that A is diagonalizable. And moreover, I want to write the eigenvectors themselves as v1 up to vn. And I want to write the inverse of that eigenvalue matrix by row, w1 star down to wn star. And so v inverse v is the identity, so you can see wj star Vj will be 1, and Wj star Vk will be 0 if j is not equal to k. So let's substitute in that diagonalization. And then we can multiply by V inverse. That's a constant matrix, so we can pull the derivative outside of it. Like that. I can call this V inverse x. This is just a change of coordinates. And it's a change of coordinates. If it's a nice symmetric matrix, an orthogonal change of coordinates. If it's a non-Hermitian matrix, then maybe it's a kind of pinched new coordinate system in which our system evolves along the coordinate axes. And that's the key of diagonalization. It's taking a hard problem that couples n variables together and to evolve in an intricate intertwined way, and picking a coordinate system in which the problem is trivial. And we end up with a bunch of simple linear systems, yj prime of t equals lambda j y of t, that we can all solve, of course, as, yj of t is e to the t lambda j yj at time 0. And so then that allows us to write the entire solution x of t as v y of t. And one nice way to do that is as the sum from j equals 1 to n of e to the t lambda j. Now I need some way of resolving that yj of 0, since y of t is v inverse x of t, then y of 0 is v inverse x of 0, which is this matrix of w1 star down to wn star times x naught. And so each of these individual components here look like wj star x naught. And this component will play a big role. It tells us how much our initial condition is disposed in the jth eigendirection. And so we have evolution e to the t lambda j. Then we get this wj star x naught. And then we get the eigenvector vj. So here's our coordinate vector. Here's the initial condition. And here is the evolution in that coordinate direction. And so now we can immediately see how this system will evolve in time. Right? There could be some early cancellation where these different and perhaps non-orthogonal vectors kind of collide. But as t gets large, what will dominate? The rightmost eigenvalue. Okay? So as t goes to infinity, this is dominated by the rightmost eigenvalue in the complex plane. Largest real part. Yep. And of course, if it's complex, then because A is symmetric, there'll be a pair of those. And so maybe, and maybe we want to make sure we compute the rightmost, and so maybe we don't just want one, we might want the 10 rightmost eigenvalues, and then to study how the problem evolves in that eigenspace. And so this is a problem for which we can answer a stability question by saying, is the rightmost eigenvalue in the left half plane, so we get decay, or is there an eigenvalue in the right half plane, and if it is, how far in the right half plane is it? And so this is a case where we might want to compute just one particular, or a handful of rightmost eigenvalues. So this is one trait. And often when we seek eigenvalues of a large-scale problem, always, we have some property in mind. We don't just want to find 10 eigenvalues of this big matrix. We want the 10 that have, say, the rightmost property. The next problem I'd like to introduce will look quite similar, and I introduce it for historical purposes. That will become evident shortly. If I have a second derivative, and I will again specify the initial condition, and I will start out at velocity 0. So I have a position and 0 initial velocity. I can do the same trick with the diagonalization and the coordinate transformation. I get a diagonal problem, but now it's y double prime equals minus lambda y. And so that's now a second order scalar differential equation. We can write down the solution in the y components. It would be cosine of the square root of lambda j times t times that same coefficient that describes the initial condition, and then that's it for the y equation. And then the x equation becomes the sum. J equals 1 to n, cosine square root of lambda jt, wj star x 0 times vj is the vector. So we get a linear combination of these oscillating components here. And this is If we had a non-zero velocity, we'd get sign components in there as well. And now maybe it's less obvious which one dominates because we get just oscillations at different frequencies. But what we might expect, well, we should maybe look at an example to build some expectations. So, yeah.
How do you decide which square root?
Well, oftentimes, yeah, that's a fair question. Often this example comes up when A is a self-adjoint matrix with positive eigenvalues, and so that question's moot. But yeah, that would be an important question in general. I didn't. Yeah.
If lambda j is complex, you could still have it.
You can still make sense of this, or maybe you prefer to write these in terms of Cauchys, and there are things you can do if that makes sense.
So you assume here that lambda j are positive because.
Sure. In many cases for this problem, we have that nice case. And if we could go to the screen now. My friend Steve Cox told me about, forever it will be part of Simon's lore. I showed you some 17th century science last time. I moved forward to the 18th century here. My friend Steve Cox thinks this is the first example of eigenvectors being computed. So Daniel Bernoulli was working publishing in the Royal Academy of St. Petersburg in 1733, and he was interested in some very basic questions of simple mechanics and made groundbreaking work. Imagine a thread that holds two masses, and Bernoulli asked, is there a way that we could displace those initial masses to the side so that when we release them, they go through the vertical at the same time? And so is there a way to do that? You might say, yeah, there's a way, maybe something like this, and they would swing through and back and forth. But maybe there's another way, right? Maybe I could have one mass to the right, x1, and I could have a negative value of x2, and then maybe they would swing back and forth like that. And so Bernoulli proved a theorem where he calculates what the ratio should be between the two displacements that would give us this behavior. And of course, this is a century before matrix notation was used, so he doesn't describe eigenvalues and eigenvectors or anything. But what he is finding is that the ratio of BH, or of CF to BH, should be like 1 plus or minus the square root of 2 to 1. So this is the first matrix whose eigenvectors were computed. And there they are. 1 plus root 2, 1 minus root 2. The eigenvalues are 2 minus root 2 and 2 plus root 2. And I hope I didn't put those in the wrong order. I think maybe I put those in the wrong order. This is the smaller one, meaning it oscillates slower. And this is a larger eigenvalue giving us faster oscillation here. So what Bernoulli didn't do, Clifford Truesdell talks about this work, he didn't realize all motions could be broken down into the sum of these two components. He didn't realize you could superimpose the eigenvectors and get the motion of any initial displacement. But still, this is groundbreaking work. And he wasn't satisfied with just two. Well, first of all, there's the computation. I think he did a pretty good job this plotting. 3. There they are. So the 3 modes of a 3-mass system with equal weights and equal distance down the string. And he describes doing these experiments with masses where he prevented the lead from forming in the middle, and he put a thread through them. And he doesn't say how he released 3 masses at once to verify this experiment, but somehow he did. And in any case, you can do this experiment. I've had students build apparatuses to test this out and use webcams to track the beads, and you do get, indeed, eigenvalues where you should, so for small displacements. And so the first eigenvector is coming from this problem here. Okay, back to the board. One last problem that will be equally simple or even simpler that Nikhil already hinted about. Well, I don't know. Maybe you have, 1733. Maybe you're curious about how to play with pendulums. I don't know.
Related to club strengths?
What's that?
Is it related to club strengths?
It was being done in the same era of looking at, say, beaded strings and so forth. Yes, yeah, very very similar from that same era of mechanics. That paper is sandwiched between two papers by Euler in the journal, and that was definitely a rich era of amazing progress. And Truesdell has a volume he wrote that's included as one of the volumes of Euler's collected works that works through summarizes the history of the mechanics from that era. That's just really very interesting. Okay, so the last example I want to describe, maybe I shouldn't have erased everything. We saw already in the context of what Nikhil called the power method. So I'll have a discrete time dynamical system, again with some initial condition. And again, we can solve this in the same way. We diagonalize, we change coordinates. You'd get now your yj at the k plus first step equals lambda j times yj at the kth step. All of that will lead to an expression for what xk looks like in general, the sum from j equals 1 to n of the jth eigenvalue to the kth power times our normal coefficient here, our usual coefficient, times the eigenvector vj. Okay, and this expression, which deserves a box, if we think about this, it's easy to see which eigenvalue will dominate, right? That will be the one with largest magnitude, right? And eventually, as we take more and more powers, this vector should align with the dominant eigenvector. And so this then suggests to us the first algorithm, because these steps are so easy to apply. This suggests an algorithm for computing that dominant eigenvector. So let me make an assumption that the absolute value of lambda 1 is greater than lambda 2. Then it's a fight. Yeah. Yeah, absolutely. And in that case, you better not go looking for 1. You better go looking for 2. Let's assume it's not the case, just for simplicity. Of course, these dynamical systems come up in Markov chains and compartment models and population dynamics and so forth. So many examples here. So let's look at the power method. Okay, so it is the power method right here. This is it. Maybe we want to make a slight modification. Maybe we want to worry about if one of these is, say, growing or shrinking, and all of them are shrinking, or one of them is growing. Maybe this vector gets a little out of control, and so we can choose some way to normalize it, just to control the round off without, or the overflow or underflow, without changing the direction. And so when we think about algorithms for computing eigenvalues, actually what we're often thinking about is eigenvalues, algorithms for computing eigenvectors or invariant subspaces. And then the consideration is how does this vector align with the eigenvector that we're trying to compute? And that's how we study convergence. And so we'll measure convergence via the sine. Okay, so the sine of the angle formed between the eigenvector we're trying to compute, so v1, the eigenvector associated with lambda 1, and our approximation xk plus 1. Or xk, let's just say xk. And since we're only interested in direction, it will suffice to just not worry about the normalization. How do we define the sine of this angle? Well, I think a picture kind of illustrates things. Suppose we have our eigenvector v1 here, And I didn't state it earlier, but it's a natural assumption to assume that the right eigenvectors are normalized to be unit vectors. And then I have some approximation here.
So I guess you're making some generosity assumption on x0.
Absolutely. Yeah. Well, or we'll see where we'll need that.
Otherwise, someone
Yeah.
malicious could
Absolutely.
make something perpendicular.
Exactly. If I start with something for which this coefficient is 0 and there's no component in V1, game over, right? Now, I might benefit from rounding error that introduce a little whiff of this, and if that eigenvalue is strong enough and I take enough steps, that rounding error will get magnified up to a dominant point. But in theory, yes, I have to always have a caveat that my initial condition isn't pathological.
You might also benefit from randomness.
You could, definitely. And so for decades and decades and decades, this algorithm has been run with random vectors before we knew that the cool kids called this rand-NLA. Yeah. Okay. So the sine of the angle will, we think of just trigonometry, right? We can motivate the definition. We'll look for the best approximation. Here, some, say, alpha times xk. And then the sine of the angle will be the opposite. So this would be v1 minus alpha xk in length. And this is the length of v1, which is 1. And so the sine of this angle will be defined to be the minimum alpha, such that the norm of v1 minus alpha xk, like that. Okay, so, and we like sines rather than cosines because as the angle goes to 0, the sine will go to 0. Right, and so that's a nice way to think about convergence. And so I'd like to actually prove a convergence bound for you that's a concrete upper bound rather than the asymptotic bounds that are more common to see in the literature, and then we'll see the asymptotics come out of that, at least for this one simple case. Okay, and so let me think about this expression here. I'm going to write out my formula for xk and see if I can find a strategic way to bound this by picking alpha. Okay, so this is still the minimum over alpha of v1 minus some multiple of the sum from j equals 1 to n of lambda j to the k, wj star x0 times vj. And my goal is to capture v1, right? And so I might think about the way to choose my alpha, perhaps suboptimally, to knock out v1 entirely from this formula, right? So what would I'd take alpha to be? Let's see here. Shouldn't block the formula. So the amount of v1 is lambda 1 to the k w1 star x0. Here we see your question. Let's pick alpha to be 1 over lambda 1 to the k w1 star x0. We're assuming w1 star x0 is non-zero, right? And with this suboptimal, potentially, likely choice, I get a bound. Subtract, I knock out the v1 component. What I'm left with is the norm of the sum from j equals 2 to n of lambda j. Maybe I want to put lambda j over lambda 1 to the k. And maybe I want w, well, I should be careful about absolute values here. Okay. Savor this formula for a moment. Yeah. How does the power method converge? Well, first of all, the bound gets worse the smaller and smaller this coefficient is, right? So the less emphasis I have on that first eigenvector in my expansion, the worse the bound gets, right? So the initial condition will have some kind of delaying effect, potentially, or accelerating effect. Maybe I have some really good estimate from a smaller discretization or from physical knowledge or an asymptotic expansion that lets me pick a really good x0 that's closely aligned with my eigenvector. What's the benefit? The benefit comes in a small value, a very large value in that case of w1 star x0. But it's only showing up as a constant. The convergence rate is going to be determined by how fast this numerator goes to 0 relative to the lambda 1 to the k and the denominator, right? And I can now kind of do the common thing one sees in books, which is to say this behaves something like lambda 2 to the k over lambda 1 to the k. But these statements do a little disservice to the interesting dynamics that can be happening in the numerator here. But this gives us a sense of how fast this converges overall asymptotically. And we might call this an eigenvalue gap, which you'll hear many people sort of talk about. The separation between two eigenvalues being the crucial element accelerating or decelerating the convergence, dictating the convergence rate, and how well separated is one eigenvalue from another. Okay, any questions so far? Yeah, Jim.
So, were you going to tell the Gene Golub office hours story?
No, I don't know it.
So, Gene was having office hours one day, and a student he didn't know walked in and said, I have this really enormous sparse matrix, and I need to find the dominant eigenvalue and eigenvector. And so Gene took 5 minutes to explain the power method, and the student said, thank you, and walked out. And a week later, Gene came back and he found an envelope under his door with a bunch of startup stock for some company he'd never heard of before, called Google. Very wealthy from 5 minutes of office hours.
So we should all invest in our students.
Mark, I wonder, Mark, you assume that A is a real value?
I assume that A is real value, but there's nothing in this analysis.
Because then you have to be careful with the assumption because they have two dominant complex eigenvalues.
Absolutely, yeah. So what happens, for example, if A is real valued, but the dominant eigenvalue is actually an eigenpair complex conjugate eigenvalues, right? Well, so I'll touch on that in just a second. First, let me just think that if I'm unsatisfied with this convergence rate, or maybe I don't want to, for my application, compute the largest eigenvalue. Maybe I want to compute the smallest eigenvalue. There are various other strategies that one could do. So first of all, we know that shifting A, so replacing A with just a constant multiple of the identity, just shifts the eigenvalues. And so I could shift things around if I like. But even better, I can invert that problem. And that turns eigenvalues close to mu become largest magnitude eigenvalues. And we call this idea inverse iteration. And this is just basically the power method with A minus mu I inverse x of k. But as we discussed yesterday, we don't like to compute inverses. So this is equivalent to solving a system, A minus mu I xk plus 1 equals xk at every step, right? And so maybe I have one of those LU factorizations of A minus mu I that I can apply repeatedly to make this work. Now, some of you are thinking, what if I change mu at every step? Maybe based on some kind of eigenvalue estimate, which we'll talk about in a second. Then you have something called Rayleigh quotient iteration, which has really fascinating and complicated convergence dynamics and chaotic behavior and so forth, and has close connections to Newton's method. But this is a simple idea here. We want to go a little bit farther because we're concerned about that complex conjugate pair of eigenvalues. Then so yeah, gosh, thank you, yeah. Good, yes, that's what I meant. Yeah, that's very important. Yeah. Yeah, and so then in this case, the convergence rate will behave like, well,
Could you not write there?
oh, I'm behind. Yeah, okay, well, okay. Good, thank you. Okay, but you can see this. We solved that system. Okay, good. All right, so let me just start up over here with the next algorithm. And I'm only going to say a few words about subspace iteration. And this is the natural way to generalize the power method. Instead of starting with just a single vector x0 in Rn, now I'll start with a block x0 in Rn by m for some m that's larger than the number, at least as large as the number of eigenvalues I want to compute. So if I'm worried about a complex conjugate pair, maybe I choose m equals 2 there. And then you can imagine how this iteration will proceed. I can just apply a to xk, and then I can get xk plus 1 now is the normalization by orthogonalizing that. And there are all kinds of variants based on how often you would do this orthogonalization. Maybe you basically do powers of a applied to one xk and then orthogonalize after applying multiple powers. There are various ways you can now look at convergence. You can look at the gap between lambda m plus 1, lambda m over lambda m plus 1. If you want to know how the whole subspace is converging to the m dominant eigenspace. But you can also ask, well, how well does this eigenspace that I'm approximating, this approximate subspace here, how well does it approximate the first eigenvector? And you can get more refined bounds that involve subordinate eigenvalues and not just the mth one there. Because maybe within this subspace, you're capturing individual eigenvectors at different rates. Okay, so that's a whole subject in its own right. But what I'd like to devote a fair amount of time here to is another generalization of the power method. Yeah.
We had the case m equals 1.
Yeah.
This ratio was lambda 2 over lambda 1. Right?
Yes. Yes, I should have this. Thank you. Yeah. Started writing it that way. And yes, that's what I want. We want it to converge.
Mark, I have a really basic question.
Yeah.
Which is like when you were giving us the differential equation example,
Yes.
what you wanted was the rightmost eigenvector value, not the maximum.
Right,
magnitude.
right.
Maybe this is what you were getting at with inverse iteration, but like, what would the standard method be if I just want the rightmost eigenvector?
Right, in that case I might, that's actually a really subtle question that people have spent quite a bit of time thinking about, because I might just say, well, what if I just choose mu equals 0 and do A inverse, because I'm thinking of that rightmost eigenvalue maybe being close to the origin. That's one thing you could do. There are more sophisticated sort of linear fractional transformations or Mobius transformations that you can apply, where you kind of combine this A minus mu I inverse with an A plus sigma I to do other transformations that try to turn kind of lines in the complex plane into circles, and anything on that circle will have largest magnitude. So there are more sophisticated spectral transformations that can be accomplished when you're searching for rightmost eigenvalues. But
it's
unlike,
a bit of an art. It's not like there's it's
Yeah.
not like if I ask for it, there's some algorithm that I'm using.
it's not as nearly as clean as in the discrete time case. Yeah. Other questions?
The sign bound,
Yeah.
if the eigenvectors are really skewed, could this be huge?
Yeah, that could be huge. And then maybe our inequality is bad because I'd hate for the sign to be larger than 1. And maybe I need to take k pretty far to get this to be disentangled. Yeah. Okay, so.
So maybe just follow
Yep.
up on that earlier question. So would it be fair to say that in some intuitive sense at least, finding eigenvalues close to 0 is somehow complicated to solve the linear system with the matrix A? In difficulty, I guess, or?
In the sense that you'd be maybe applying A here with mu equals 0, for example, many times. So you'd be reusing solving linear systems a lot. Yeah. Good point. Yeah.
Stated in terms, is this like run the random walk on a graph, and then by adding this ui, you add loops to each term, so you make it far away from a bipartite graph where you have two competing eigenvectors?
Yes, that's a nice, in terms of spectral graph theory, that's an interesting way of thinking. Essentially, that's what you're doing here. I don't have a good interpretation for what the inverse transformation looks like in that sense. Okay, we'll talk about Arnoldi's method. I'm using red here. So we've moved from 1733 to now 1951. So we're here in modern times. This algorithm can be motivated in the following way. I have my power method iterates. I had x0, I had a x0, I had a squared x0, and so forth. And so maybe I think rather than just estimating kind of a single vector here at a time, maybe I want a larger subspace, and I can get that subspace as the span of all of these power method iterates. And for purposes that will become clear maybe a little bit later, I'm going to change my starting vector to b, and that will make a little bit things nicer when I talk about GMRES. So maybe I look at the first k of those power method iterates, and maybe I should give this subspace a name. We saw it yesterday. It's the Krylov subspace generated by A. And so now I'd like to not just work with a single vector, but with the span of all those vectors. Now we can get into subtleties about properties of B that ensures that this has full rank K. For example, if B is an eigenvector, this will have rank 1. But we'll generally be thinking about working with generic B so that we can keep building up this dimension, at least until dimension n, when we're going to run out of steam in n-dimensional space. And now what I would like to do is find an eigenvector estimate from this subspace. And just as I generated an orthogonal basis for the subspace over here, so I will want to generate an orthogonal subspace basis for the subspace here. Because if I think about this, knowing what you do about the power method, what do you think about those vectors that form the basis? They're lining out, Joel's lining up with the dominant eigenvector. So each of these basis vectors is converging. So if I just naively ran a bunch of steps of the power method and then tried to use that to get some eigenvalue estimates, I'd be in bad shape for most A. And so the key part of the Arnoldi algorithm is building an orthonormal basis for the Krylov space. We have a way of building orthonormal bases, right? Given a set of vectors, Gram-Schmidt process. And so Arnoldi's method is a variant of the Gram-Schmidt process for orthogonalizing power method iterates, essentially. And so I'd like to kind of just walk through that quickly. So if I'm given Q1, Q2, up to Qk as an orthonormal basis for K sub K, I want to find the next vector. So I'll get the next vector by first of all generating a vector, the next vector in my subspace. So one option would be to take a to the k times b, which would be the kind of the next vector to expand my space. But I have a better option there, which is to apply q, a, to my last of these basis vectors. So q1 through qk are contained within this space. Qk expanded the space, so it has some component in a to the k minus 1b. So multiplying it by a, well, it's guaranteed to expand the space unless b is somehow deficient. So here's my new vector that expands the basis. And now I just need to remove the stuff that's orthogonal that I've already captured. So I can do that by just removing the orthogonal projection onto that vector, where here I'm using qk, the capital QK, to just be my n by k matrix of those basis vectors. Okay, capital QK, QK star is the orthonormal projector onto the Krylov space, and so that removes what needs to be removed. Okay, A times Q is a vector, K. Thanks, yeah, okay. What's that? I love it, I love it. Like I said last time, watch me like a hawk. Okay. So, we have this nice statement here. I'm going to make a few notational definitions. I'm going to set little h sub k to be equal to qk star times a qk, which is a vector of length k. Okay. And then I'm going to build up a large matrix, capital. Let me define one more thing. This will generally not be a unit vector, right? There's nothing in here that normalizes this, so I'm going to give qk plus 1 a little hat, and I'm going to define qk plus 1. First of all, I'll define hk plus 1k to be the norm of qk plus 1 hat, which I'm again assuming is non-zero because I've expanded my space. And then I get qk plus 1 equals qk plus 1 hat divided by the norm of qk plus 1. Okay. And then the last ingredient that I need is a matrix that I'll call hk tilde, which will consist of hk minus 1. So it's a recursive definition. Start with an empty hk. It'll put in this hk, a 0 block, and then this scalar hk plus 1k. So this will be a matrix of dimension k plus 1 by k that just accumulates these Gram-Schmidt coefficients, right? This qk star aqk, hk vector. Each element of hk tells me how much of each vector in Q to remove. That's the...
I'm getting a little lost.
Yeah.
I'm fine with the second panel, but what are you doing in this third panel?
Okay, I'm just defining some stuff.
Are you missing a hat in the...
Yeah.
on the right?
There we go. And
Okay, so you'll tell us
there we
why
go.
you're doing it?
I'll tell you in a second, right here, on this panel, and I have only half a panel, so.
Okay, let's see what this is.
Okay.
It was fine with this.
Okay, so the second panel is fine.
I'm going to define qk plus 1 as qk plus 1 hat divided by the norm of k plus 1 hat.
Yeah, and in fact, I could just write this here as hk plus 1k.
Yeah,
Yeah.
I don't know why you do this. H is...
Yeah,
Okay.
all will come clear here in a second. So look at this boxed formula. Okay, bear with me. Boxed formula there. I'm going to now write that as qk plus 1 hat equals, in fact, another way of writing qk plus 1 hat that I like. I'm really going to try your patience. Right? That's just another way of writing qk plus 1 hat, which is now aqk minus this qk times my hk, like that. Or said another way, aqk equals qk hk plus hk plus 1k qk plus 1. Okay. So I think that's a beautiful formula.
How is that improving the quality of my life? You have this nice algorithm, and then you write back.
It's for analyzing too.
For analyzing what's going on. Okay, so this is going to hold for all of my k. So this holds for all values of k. And so, in particular, it held when k was 1, and it holds when k is 2, when k is 3, and so forth. And so, just because of time, I'm going to have to ask you to make a little bit of a leap of faith. So this could also be written as hk plus 1k, like that. If I stack all of these things together, I get this beautiful relationship here, that AQK can be written in these two equivalent, very simple, compressed ways that describe the entire Gram-Schmidt process applied to A with the Krylov subspace A and starting vector B. So I'm applying A to each column of this orthonormal basis, and I'm writing that as that same orthonormal basis times the Gram-Schmidt coefficients plus the normalization factor times that last vector. And if I'm willing to put in that extra, append Q with that extra latest vector, then I can consolidate everything in this K plus 1 by K matrix. And this matrix has what we call upper Hessenberg form. So for example, if K equals 4, this matrix has 4 entries in the non-zero entries in the first 2 rows, 3 in the second, 2 in the last. And so the zero structure here, which builds as K builds, is the fact that my Gram-Schmidt process basically only takes into account the vectors I've seen already, right, when I form each new vector. So I can't take into account Q5 when I form Q2. Okay. And the only other caveat maybe worth making here is that Q1 is the B divided by the norm of B, just to get things started. Okay. I don't know if your life's improved by that, but okay. So let's then try to improve your life. If I want to get an eigenvalue estimate from a vector, I have this notion of a Rayleigh quotient. Which, for example, for the power method, I could get lambda k as xk transpose a xk. Might just put star there in the case we, for some reason, have a complex vector. So this is a way of taking an eigenvector estimate and turning it into an eigenvalue estimate that we use all the time. And of course, we have this normalization. And if we're normalizing this to be a unit vector, we could ignore that. In the same way, for Arnoldi, we have a generalized Rayleigh quotient, which we would get from qk star a qk, compressing the matrix A to its k-dimensional Krylov subspace using an orthonormal matrix. So in some sense, we're dividing by k star qk, the identity, if that made any sense. But now if I come over to this formula, this in the box, and I smack it on the left with qk star, then I get qk star qk. I have an orthonormal basis, so that would be the identity. hk, then qk star times qk plus 1. But I constructed qk plus 1 to be orthogonal to qk, the columns of qk. So that will be 0. So qk star a qk is just a qk star qk, hk plus hk plus 1, k, qk star qk plus 1. That's 0. That's the identity. What I'm left with is hk. this, say, 4x4 Hessenberg matrix right here. So the Gram-Schmidt coefficients in the Arnoldi process give me the compression of my matrix by large n by n, million by million matrix to some k by k subspace. And then I can compute the eigenvalues of HK and use those to approximate the eigenvalues of A. But
So I still don't understand the computational advantage of computing HK versus computing that product of those three matrices.
In terms of computational advantage, just in the act of forming QK, you have HK as an artifact. So if you had another Landsberg method for computing,
It's the same computation.
yeah,
Okay.
it's just this is the board you didn't like was basically the bookkeeping board assembling that from the pieces we already knew. Yeah.
But for the symmetric case, there does be, maybe you're going to cover this, there does become a computational advantage to like doing, using your Arnoldi process.
Yeah. Okay. So there's so many directions to go.
I'm not saying you should cover it.
No, I was intending to. In 7 minutes, 8 minutes. Okay, first of all, this statement should be offensive. Because there are only k numbers here, and there are n numbers here. So what does it mean to say k numbers approximate n numbers, right? So you should argue, I mean, that was a complaint you could have made against my lecture here, and you didn't. So thank you for sparing me that critique. That's one issue. Gosh, I have to resolve the question about symmetric A very quickly. Because we only have 7 minutes left, and I want to talk about several other variations here. We can do it. Maybe not do it justice, but okay. So. So I think Arnoldi must have been inspired to develop his algorithm by the Lanczos method that appeared a year earlier. This applies to symmetric A. And so if A is symmetric, then what if I take HK transpose? QK transpose A, QK. Star, I'll put stars here. Try to be consistent. Well, that's QK. I apply the conjugate transpose in reverse, right? QK star, A star, QK star, star. 2 stars get me back where I started. A star is A. So I get QK star A QK, which is just HK. So the conjugate transpose of HK is HK. But remember, HK has this Hessenberg structure. So what does that mean to be symmetric in Hessenberg? If I know these 3 bottom left entries are 0, then the upper right better have 3 0 entries. Okay? So HK is tridiagonal. You can skip many Gram-Schmidt steps. Most. All but 2. Yeah, I'll just say most. You have a 3-term recurrence. The proof is, I just gave you a kind of a crude high-level proof. You can also show it using the same argument you used to show that orthogonal polynomials on the real line have a 3-term recurrence. Anne Greenbaum did some beautiful work on understanding how that accommodation, knowing that those are 0 and really taking them to be 0 and not computing them, that adds some instability to the process, that gives you the ability to compute multiple copies of single eigenvalues, simple eigenvalues, called ghost eigenvalues. It's all in the branding, right? And Anne explains how these ghosts can be understood by thinking about applying Lanczos to a larger matrix. I think I have that. Is that accurate? Is that high level? Okay, sure. Talk to Anne for many more details. Okay. Okay, 4 minutes. GMRES. I said I promised you last time I would say something about how GMRES actually works. So remember, we're trying to minimize the norm of b minus a x hat for x hat in the kth Krylov space. Well, another way of writing that now is minimizing over C, b minus a qk_c, right? Because anything in my Krylov space is in the span of its columns of my basis. But now, AQK, I've got a handy-dandy formula for AQK. There was a reason for doing that. So,
C is height k, is that the point?
what's that? C is of length k, yeah. Say. Much smaller. Right. If we can somehow, it's still length n vectors, though. Still length n vectors, but AQK, that's qk plus 1, hk tilde, which is, remember, this nk plus 1 by k extension of the Hessenberg matrix. B. I guess I erased it, but you might recall at some point I said that Q1 was B over the norm of B. So another way of writing B is as the norm of B times qk plus 1 times the first column of the identity. Like that. Now I have a qk plus 1 in front of both terms, but that has orthonormal columns. And remember, I'm always working in the Euclidean norm. And so the Euclidean norm is invariant to orthonormal changes of orthonormal basis, right? And so I can pull that qk plus 1 out and not lose anything. And now I have a least squares problem.
I missed why you have this E1.
Because I need to pluck out the first column, Q, little q1.
E1 in RK.
Yes.
RK
Plus 1.
something. Yeah. Okay.
Yeah. Sorry, I was going fast. Least squares problem of size k plus 1 by k. And so this is how you can actually compute the GMRES residual iteration. You get the C vector from solving this small least squares problem, and there are even slick ways to do this that don't even require you to actually do much work. And then you form your xk, or x hat, if you will, from qk times the least squares solution. There's your GMRES, all from the same process. Okay, but there's more. Can I have 2 minutes more to answer this question about which of these? Okay. I'm at the mercy of whatever my initial vector B was in terms of how the eigenvalues of HK might resemble those of A. And I'd like to do something about it. I want to control the process. I don't want to take K to be too large because that gets very expensive, storing all those big, long, n-length vectors. And I also want to somehow tune my B. So I'm going to compute the eigenvalues of HK. Well, I'll call it HM, for M being larger than P, which is the number of eigenvalues I want. So I want to compute the p rightmost eigenvalues, say. Call these theta 1, theta 2 to theta p, and then theta p plus 1 up to theta m. The first p resemble the eigenvalues I want. The remainder don't. Okay, so in a sense, I want rightmost eigenvalues, so I'll just sort them by real part, and I'll choose the p rightmost to be the first ones, and I'll choose the other ones that I don't really care about to be ordered last. Then the restarted Arnoldi process simply does this. It says,
So you need this M because there's probably some error, or you're worried that asymptotics haven't kicked in yet or something?
Well, this is in some sense a buffer. I need at least one of these for the whole thing I'm about to describe to work, but usually I might want m to be 2 times p. That's a rule of thumb that's often recommended. I'm going to form a polynomial of degree m minus p. And then I'm going to get a new starting vector. I'll call it b plus, which will just be phi of a times b, which if I go back to my kind of usual way of writing things that I started at the beginning of this lecture, I'm going to get a new starting vector, and the idea is that this polynomial is small, hopefully, on the unwanted eigenvalues. Right? These are kind of resemble unwanted. You don't. In the Hermitian case, you can guarantee because of interlacing that they are, that you'll never get these roots actually appearing where you want eigenvalues. In his 1992 paper, Danny Sorensen invented this scheme called exact shifts, showed how to implement it stably numerically using the implicitly restarted Arnoldi algorithm, and he proved convergence for this method for Hermitian A. And in the intervening decades, no one has proved a complete convergence theory for nonsymmetric A. And I just want to close by showing some illustrations of what can happen. If I can go to the screen again. What's that? With the marker, with the marker. It might be fortuitous. I was hoping that Bernoulli had called this H, called it F. Sorry. Okay, so this is the way the algorithm should work. I've got a set of eigenvalues. For those of you aficionados, do you realize the distribution of this, this matrix from its spectrum?
Random matrix?
Random matrix, Gaussian. Okay. 1 over root n standard deviation. Okay. Here are the eigenvalues. Suppose I want the rightmost 5 of them. So the red ones I don't want. Many, many more unwanted eigenvalues than wanted eigenvalues. I want those 5. So I run 15 steps of Arnoldi, and I get these black circles as my eigenvalue estimates. And they tend to be around the periphery of the spectrum initially, just like we see here. There's no, B is a random vector, so there's no bias in B that I'm aware of. And so then to follow this procedure, I'm going to say I want 5 rightmost eigenvalues, so I'm going to pick the 5 Ritz values on the right and call those approximate eigenvalues. Some of them approximate the wrong eigenvalues, maybe, right? And I'll call the other 10 my undesired eigenvalues. I'm going to use those as roots of this polynomial phi. Here's a heat map of that polynomial phi. It's got all these roots over here, so it's small in magnitude on this portion of the spectrum, and it's larger in magnitude here. Now you say, there are plenty of bad eigenvalues that I haven't damped out very much. sure, true. I'm only using 10 roots here. But that has the effect of kind of pushing your hand on the scales a little bit so that B plus now is enriched, hopefully, in these eigenvalues. And so it's not perfect. It doesn't solve the problem. But instead of having eigenvalue estimates out here, now they come closer in. Okay, so here we had one that was way up here. Now there's still an eigenvalue estimate there, but it's one of the bad ones. So of course we can repeat this process using these as our roots and get another filter polynomial that aggregates with the first one, and eventually any of these annoying eigenvalues that we haven't kind of resolved will show up as a Ritz value or something close by, and we will eventually damp it out. And we can constrain the size of our Krylov subspace to be, say, dimension 15, and compress back down to a dimension 5 and back to 15 and so forth, and drive these blue circles to the desired eigenvalues. And that's how the restarted Arnoldi algorithm works. Now in the symmetric case, it works like a dream, because this is no restarts. This is just taking a different matrix with eigenvalues 1, 1.5, 2, up to 10, red lines. My Ritz values are the black circles at step 1, 2, 3, 4. It looks like one of those Galton boards here a little bit, dropping the beads down. Okay, any case. What we see, two Ritz values getting driven out to the edges. They're approximating these extreme eigenvalues very well. The interlacing theorem guarantees that I don't get too many eigenvalues at any level. Like I don't get an eigenvalue here and then another one in this gap. I can't do that by interlacing. I could get another eigenvalue here in this gap, or I could get two eigenvalues here and none here, but they can't bunch up at the ends. And so this is what allows Sorensen to prove that this process converges for Hermitian A. The picture for non-Hermitian A, I've just taken the same matrix, diagonal matrix with those eigenvalues. I put 4s on the first superdiagonal, all distinct eigenvalues, diagonalizable matrix. Here are its Ritz values, but I only show you the real part of the Ritz values now. And you see we get some that extend well beyond the limits of the spectrum even. And eventually they all line up when I project my 20 by 20 matrix onto a 20-dimensional space, but that's just what should happen. It's a similarity transformation at that point. I need to go into the complex plane, maybe at this step 12, to see what's really going on. Here's the numerical range we talked about yesterday. It extends well into the complex plane, up until about 4. The Ritz values at step 12 are this set of black points here. Only one of them's real. That's why you saw fewer than 12 points on that line, because many of them are conjugate pairs. So how can I say resemble the good, resemble the bad for this problem? That's, okay, I close with just one last example. Jürgen Deutner-Tebbens and Morant have a beautiful paper showing how you can construct monsters that give you really bad eigenvalues of your HK, even if your eigenvalues of A are very different. And this builds on a machinery that Ann and Ptak and Strakos invented back in the 90s. So here we have an example, just a 7 by 7 matrix right there. It's got some suspiciously large entries in it. Starting vector, very nice. My eigenvalues of A are the integers minus 8 to minus, I guess minus 7 to minus 1, whatever, minus 8 to minus 1. And that's an 8 by 8 matrix. And here are the Ritz values at steps 1 through 7. 1, 1, 2, 1, 2, 3, 1, 2, 3, 4. These are in the right half plane. These are all in the left half plane. This is about as nasty, as bad as it can get. They have a construction to allow you to build monsters with whatever Ritz values you want. And this gives you a glimpse of the challenge of convergence theory in the non-symmetric case. And I'll talk more about that on Tuesday in one of our internal seminars. Thank you. Sorry for running late. Yeah.
Regarding the starting vector over there.
Yeah.
So we don't know these thetas. We don't have the phi. So how can we choose that?
Well, we're going to compute the eigenvalues of HM, say. So we do the Arnoldi process for M steps.
Yes.
We compute the HM eigenvalues, M of them. Small problem. Nikhil solved it. You've solved it, right? Okay. And then we sort them based on their properties. So we want the rightmost eigenvalues. You take the...
So is it so You say we have the eigenvalues, now we want to do eigenvector
No, we have the eigenvalues of HM.
of HM.
Yeah. Okay, and we're going to use those to help get the eigenvalues of A.
These are the eigenvalues of HM.
Of HM. Yeah, they resemble the unwanted eigenvalues of
Then
A.
you say I want to focus on like the first one or something.
Exactly. So I'm going to, I mean, this
I see. Okay. Good.
plot here, I think, really kind of hits what's going on. Here we have,
I
these are the ones we want. These are the roots. We're going to filter out, trying to remove, make this polynomial small on the portions of the spectrum we don't want, so it's large on the first P of those.
I have one comment. Something this analysis reminded me when you analyze continued fractions,
Ah,
right?
well, for
Also-
Lanczos, there are deep connections
Yeah,
there.
it looks very similar. You have these such matrices, you have this. So I think it looks very analogous. So when I looked at it, it was not from the numerical point of view. There are no norms and so on, but it's
yes.
the same algebra.
The book by Leeson and Strakos on solving linear systems has about a 100-page chapter devoted to this connection.
So this is the
Gaussian quadrature, continued fractions, steel cheese, etc. It's
Then I'm happy.
masterful.
Okay.
It's beautiful. Oh,
It looked kind of similar.
yeah. Your neighbor at TU Berlin.
Oh yeah, but you know, I'm in algebra. I was put in algebra.
Just go knock on Jorg's door and ask him about continued fractions.
He should be here.
He will be here soon. Yeah.
He's not here.
Last question.
Okay, so my impression is that Arnoldi is good at converging to the largest magnitude values. Is part of the idea of restart Arnoldi to like shift our goal is saying instead of the largest ones, we want the rightmost ones?
Or whatever you want.
ones you want.
If you wanted largest, then you would choose the smallest magnitude Ritz values as your shifts. And it's all up to you as to how you classify these.
So
That's
I
kind
can
of-
like split these up by whatever thing I want. I want the ones closest to this little disk, this point.
Exactly.
Of the point.
Exactly.
Okay, cool.
Now, if you're in that situation and you're willing to invert A minus mu I or solve linear systems with A minus mu I, it's even better to apply Arnoldi to A minus mu I inverse. Just like we applied power method to A minus mu I inverse. It's called shift inverter Arnoldi. And if you have you want smallest magnitude or interior, that's a more effective way if you can afford to do those solves. But that's trading a matrix vector product for a linear solve in complexity.
Right, thank you.
Yeah. Okay. Maybe should wrap up, but I'm happy to take other questions afterwards. Yeah. Okay. All right.
So I noticed the title for today's talk is Algorithm for Large